that's going to be in the upper left. Yeah. Well, it says live right now. The time hasn't started.
Okay, then it started now. So start.
I think we are live. Okay.
Are we?
All right. Well, yeah, and it's 8 o'clock. Okay. Well, welcome everybody. This is Doug Solsley, and I'm here in Julian. We're connecting with Vivek Vijaya Kumar in San Marcos, and he's set up to do spectroscopy tonight, a star party, a sky tour, which will through the lens of spectroscopy. So, Vivek, do you want to tell people a little bit about what equipment you're using?
Are we live?
I believe we are.
Do you see viewers?
I see viewers. I see one concurrent viewer. Yeah.
Does it? So we're okay. Do you see like the icon that shows what I'm doing?
Mm-hmm.
Okay, so yeah, I've got a 11-inch Celestron SCT on a mount with a cooled color camera with the spectroscopic grating that allows you to look at, to analyze the light that comes out of celestial objects. So what we can see here right now is actually one of them, which is if you look at the very bottom, that's the star Vega, and then this shows its spectrum. So that's what we're going to be analyzing tonight. So we're just going to wait for some people to join, and then we're going to get into it.
All right. Well, we already got some more people joining. We could talk about we're going to be looking at stars, different kinds of stars. We're going to look at some planetary nebulae, and let's see what else. And a couple of planets, Neptune and Uranus, and also a galaxy, M32, satellite of the Great Andromeda Galaxy. So we're going to be looking at a variety of objects and their different spectra and what we can tell about them by the spectra, which will be Vivek's bailiwick, since he has done a lot of spectroscopy. Okay, good. We're up to 10 viewers, though. Okay, well, you can start telling people about the first target.
Okay. So this is the star Vega. Let me get it a little bit more closer in. Okay, and so this is actually looks are deceiving. It's actually a pretty blue star, and it's got it's a main sequence star like our sun. So it's a pretty typical star. It's just much more massive than our sun, and it's a little hotter, which is why it's more blue. Although the camera right now doesn't show it as being very blue. Yeah.
Oh, I forgot to mention, we want to thank Fred Delgado. This spectroscopy star party was his idea, so we're dedicating it to Fred tonight.
Is there anything on live chat yet?
Yeah, Jerry Hilburn says good evening. Hi, Jerry.
Okay. Yeah.
And just so everybody knows, Vivek is running the telescope, interpreting the spectra, and giving us commentary. So he's got a whole lot going on at his end. I'm just here kind of hosting and commenting.
Okay. That's a better view. Okay, so I think we can start.
That's an image of the star at the very bottom of the screen.
Yeah, this is unstretched, and that is stretched over here. But I'm not gonna keep. This is just the capture software. So this is what I'm gonna use to take the images of the spectra, and after that, I'm gonna take it in here to do some quick process to process it, and then we can view what the actual spectrum looks like in graph form. So first, I've started.
Okay. Oh, it says no data of the stream will end shortly unless you restart it in your streaming. Yeah, we're getting buffering, I think. I lost your sound there for a second. What do we need to do? Stream settings?
I think it's fine.
Dave Decker's on. Dave Decker is here. Hi, Dave. Good to
Oh,
have you with us.
it's not buffering on the OBS end, so I think it's fine. Yeah.
Okay, I can hear you okay now.
Okay, I'm just gonna quickly. We're gonna start taking, I think, probably just a 30-second exposure of the. Actually, I think that's a little too long. Yeah, this starts pretty bad. I'll just take a 1-second exposure. I'm just gonna save that. I'm right now guiding, which means the mount there's a separate camera looking at a star and guiding on it to make sure the mount tracks accurately. Because, you know, the Earth is rotating and we have to compensate for that using the telescope mount, and it tracks. But that tracking is always perfect, so I have a separate camera here doing that. So, okay, I think it's taking the exposure. Then you have to do this quick process.
Now you're getting to see a little of the technology involved in imaging. Anybody who's out there, let us know who you are. It helps us to know who's in the audience so we can, tailor our comments appropriately.
Yeah, I'm using a color.
We got some amateur astronomers aboard.
Yeah,
we don't know who else is.
This stream is going to be a little more sciencey and more photography stuff, so it's gonna. I don't know how hard it's going to be to follow for some people, but we're trying. But yeah, basically, I'm using a color camera to get color to be represented. But that means I have to also do something called debayering in order to get that color. So that's what I'm doing right now. Okay, it's finished. Then I can open up this software to actually examine the spectra itself. And snap. Okay.
Yeah, so there's going to be a kind of a graphic representation, but also the color spectra itself.
Yeah. You have to get the rotation right too. Otherwise, you won't be able to correctly look at the data. Okay, I think that's good. Okay. And so this is the spectrum, but it's just pixels. It's not very useful. So in order to actually turn that into actual looking at what the wavelengths are, we have to do a calibration to assign each pixel a wavelength. So let's see. Where is this? 85.
Oh, hi, Mike McKeague. Good to have you. From up in, I assume you're up in Oregon right now.
Okay, so now we can actually look at the spectra. And that's the spectra we've gotten for Vega. Pretty bright main sequence star. If you know what spectral types are, it's an A-type star. And what that means is it's pretty massive, and it's much more massive than the sun, and it also has pretty hot, which is why it has more of a blue color as opposed to our sun, which is more white when you look at it outside of the atmosphere. So, but what we can tell from the spectrum itself is trying to look at these dips. And these dips are due to the chemicals, well, not the elements that are present in the outer layers of the star. They absorb some of the light coming from the star, and they absorb specific wavelengths that are characteristic to that element. So, for example, this dip over here, we know at around 656 nanometers, we know is to be characteristic of hydrogen. And there's another line that's also characteristic of hydrogen at around 486 nanometers. So we call that one hydrogen alpha, and we call this one hydrogen beta. And there's also, then we can basically, if there's this absorption line at that specific wavelength, then we can assume that to be the signature of that element. And that's how we can look at the composition of stars, and that's by just looking at how these elements in the atmosphere of the star interact with the light coming from the star itself. So
those dips represent gas that's in the outer part of the star that's
Yes.
absorbing light. Yeah, so
Yes.
like absorption lines.
So this is basically the signature of that element in the star's light. That's how we can determine the composition of stars. And I just took that using, well, just by taking a picture of the spectra through a grating, and then just analyze it in a graphical form, and we can see that dip, and that's the signature of that element. And of course, these other dips over here, they also mean a specific, and if you can look at the wavelength, you can tell what it's characteristic of. And I think these are more metallic ones. Like in general, a lot of the lines of metals like iron or calcium, they tend to be more around the violet blue region. So that's probably what these are. But generally, the ones that are most identifiable are the ones from hydrogen, because stars are made up of mostly hydrogen.
Okay, where would carbon be?
Okay, that's something we're going to get into about carbon, because there is a particular type of star that is very rich in carbon, to say the least. We're going to get into that, but just first trying to introduce what we can tell by looking at this graph, because for a lot of people it's just going to be a bunch of ups and downs, but but these dips have meaning to them. Okay, so that's Vega. I think we can move on to our next target.
Okay, I just want to welcome, we have a couple of people from Borrego, Alan Kreutz and Marty Wax, and someone from Escondido, newcomers. Okay.
Okay. Let me stop.
Okay, so we're going on to another star.
I need to stop guiding really quickly. And okay, it's going.
Okay, our next target is Albireo, I believe.
Yep.
Okay, for the amateur astronomers, you probably all know about Albireo, but for the other people, oh, hi, Betsy Knock from Borrego, great. Albireo is a really interesting star. It's the kind of the beak of the Swan and Cygnus, and it's a very popular thing to look at. You can look at it even with a small telescope, maybe even, I don't know about binoculars, maybe large binoculars. It's a double star, and the two stars are very different, distinct in color. One is blue and the other is orange. So some people, local people, used to call it the Charger star because of the colors, but that's obsolete. It's a double star, although it's not known for sure whether it's an optical double, which means they're just two stars that are near each other in our line of sight, or whether they're actually part of a binary system, which means the two stars are orbiting their common center of gravity. And there are a lot of stars like that.
Yeah, I think people should be seeing it now. I just had a little trouble centering it, but...
Okay, well, we can see the two stars, that's for sure.
Unstretched. Well, yeah, there we are. Orange. That one's supposed to be blue. I mean, I'm in a pretty bad light pollution, so the colors aren't exactly going to be very good on these stars right now.
Okay, we have one question already from Christopher Sebald. He wants to know why so much of the element Au, which is gold, I believe, in the universe.
Can you repeat that?
He wants to know why is there so much gold? Au is gold, I believe, right?
Yeah.
My high school chemistry hasn't left. Why is there so much in the universe? I didn't know there was a lot of gold in the universe.
Well, I mean, relative to hydrogen, there's not a lot of gold in the universe. But a lot of the gold that we have in our universe, you can have some from nucleosynthesis in stars, where when they're going supernova, there's a rapid neutron capture fusion, or another huge source of gold is neutron star collisions. So the two primary sources of gold, but the thing is, on Earth, a lot of the gold that Earth has, it's because gold is pretty dense, it tends to be at the very bottom, more towards the center of the Earth than it is in the surface. So a lot of the gold we have, it's not a representative of a lot of the gold that Earth has. So it's much deeper down.
Yeah.
The density.
Okay. Okay. So we're still
Yeah.
looking at Albireo.
Yeah, I'm taking an exposure of Albireo.
Okay. So how long is the exposure?
Just 10 seconds.
Okay.
That's a bad guide star. That's better.
Okay. We got Maris Branchow from Pacific Beach. How's the moon looking, everybody? Heard it's orange. Yeah. If it's rising, it's going to be orange. It's probably just a little above the horizon right now. And last night it was accompanied by Mars, which was quite a sight.
Yeah, if anyone hears any pinging noises, that's PHD2 going, which is the guiding software. It's going to do that all night.
Okay. I didn't hear it.
I think there's a lag.
Okay, so you're debayering right now, getting the color?
I just finished debayering. Now I'm just...
Okay.
Oh my goodness. Okay, I think it's losing a guide star. Whatever. I'll turn it off. I don't need it now.
Okay.
The thing is with this kind of telescope, guiding is a little hard, to say the least.
Yeah. Okay. Well, we're watching patiently. Just so everybody understands, Vivek he's handling almost all the technology tonight because
yeah.
So bear with us and give him his due for that.
Okay, I got it. Okay, I've got the main star in Albireo. This is spectrum of the main star, and this is expected. It's an orange star. It's cooler than our sun, and although it's a more massive, it's a cooler star, which means the spectral lines are not as strong as they are in Vega. So I guess you can barely see the hydrogen beta dip from hydrogen over here, and this one's hydrogen alpha. It's not very strong either, but so that's the general trend among these kind of stars. You tend to have more stronger hydrogen lines as you get more massive and more hotter, and they're not as strong with these type of stars. But you see more metal lines, which are all of these little bumps over here. Some of these are the ones around this region over here. These are magnesium lines. So
yeah. Okay. We have Jarek Hilburn would like you to talk a little about how spectroscopy can tell us the surface temperature of a star.
Yeah. So actually, this is a good example over here. So here's the strong trend here is bluer stars tend to be more hot, and more orange, more red stars tend to be cooler. And there's actually a direct relation between the peak wavelength of the star spectrum and its surface temperature. So the lower the peak or wavelength, the more blue it is, the hotter it is, and the more the peak is more towards the longer wavelength, the more the star is cooler. So that's a direct relation. It's called, and there's different laws to describe it. But the more contemporary explanation is called Planck's law, and so there's a calculation you can do to calculate the star directly from that peak temperature. So if I took the peak from here, I could calculate the temperature of the star. The only caveat is the detector itself that I'm using. It's not sensitive equally at every different wavelength. So you have to do a response calibration to correctly calculate that. So for tonight, I can't actually just take this peak here because it's not the correct peak. But in general, that's how we calculate the temperature of stars. We look at its spectrum and see where the spectrum peaks, and that tells you the temperature of the star. And if you look at any star, if you see a blue star, you will know it's a hotter star, and if it's more orange and red, it's more of a cooler star. So that's how generally how we tell how cool or hot a star is.
Yeah, and Albireo is a good example for people to look at with a small telescope. I don't. Can you see it with the two stars with binoculars? Do you think?
I mean, if you have big binoculars, they're essentially
big binoculars. Yeah.
The big binoculars are essentially two refractors, anyways.
Mm-hmm. Yeah, or a small telescope.
Yeah.
Yeah, like binoculars are two small refractors, right? And you can really see the color difference, and then you can, in your mind, think about the temperature difference.
Yeah.
Yeah, yeah. Megan, good evening. Good to have you.
Okay, so we have now the spectrum of the other star in Albireo, and I need to just do a calibration on this one.
So the first one we looked at was the more orange one.
Yeah, and now
Yeah.
the calibration with this is, that's the thing with if you do spectroscopy, you always have to calibrate. There's a lot of calibration to it. Okay, now we got this. Okay, there's a pretty strong hydrogen beta, and there's not much hydrogen alpha, but yeah. So if you notice, I don't know if people notice, but this is the more blue star in Albireo, and you can see that in the spectrum, and
Yeah, where it's
it
bright,
has the same exact hydrogen line, and there's always more different lines. But if you notice, it's not very. There's not a lot of. There's not as much metallic lines from the metals, so that's a general trend that also occurs in spectroscopy. Okay, yeah, I think we can go to the next object.
Okay, so the main difference that accounts for the color difference is the temperature.
Correct. Yeah.
Yeah. But what about the composition? There's some difference in the composition of the two stars.
Well, it's not directly the composition; it's how strong the lines are. And hydrogen lines tend to be stronger in the more hotter stars, and the metallic lines tend to be more stronger in cooler stars. Okay, it's off.
Okay, so we're going next to a Wolf-Rayet star.
Which one is it?
It's in the Crescent Nebula.
Okay.
WR1. It's in NGC 6888, and it's Wolf-Rayet number
Yeah, this will be interesting.
136.
This is a very interesting one. Okay. Should have arrived.
Okay, should we talk a second about what Wolf-Rayet stars are?
Yep.
Okay, I can say a little bit. I did a little homework. They're massive stars, okay, and they're stars that have blown off their outer hydrogen. And there are actually a couple of types of Wolf-Rayet stars. I believe they have a really high rotational speed, if I remember right. And there's one type that's at the center of planetary nebulae, which are planetary nebulae are nebulae that are created by stars in the last phase of their life cycle, becoming a nova, collapsing and throwing out a shell of gas. We've looked at a number of those in the previous star parties. And Wolf-Rayet stars, besides being massive, they have an extreme high temperature compared to like the sun.
Okay. I'll have to go back to Vega very temporarily.
Okay, Jerry, given sunspot activity, mass ejections, so in surface quakes, can spectral observations vary because of sunspot activity? In other words, I assume what Jerry's talking about is our sun influencing the observation of
so
stars, spectral observations.
We'll actually see the spectrum of an eruptive variable star soon. So yes, we can directly observe like eruptions, like in terms of large eruptions from the star. Sunspot activity is a bit more. Yes, we can see the variations in sunspot activity in stars, but it's not very trivial. It's very slight deviations in the spectral lines that people measure, and that's how we can assess chromospheric activity on stars. But it's a pretty difficult process.
Okay, Fred has a comment or a question. He's posing, doesn't temperature also determine whether an elemental line appears in the spectra or not, which just complicates the measurement?
So what the temperature does is it affects how strong that particular line is, and
Uh-huh.
so it's not like the line is absent. It's just that we can actually. It's actually pretty useful in terms of measuring certain aspects of the star. But
Okay. That kind of Jerry was asking, Jerry Hilbert, do the deviations yield useful science? So I guess you were just
yes,
saying they
it's
do.
actually it's an active field of study. Actually, the science fair project I did this last year on was actually exactly about chromospheric activity on a particular type of variable star, and I used magnesium lines to study that, and that was with um, the more powerful spectrograph I have. For this one, I'm just using a more lower resolution so people can see the entire spectrum. Ah,
Okay. So,
yes. The go-to is acting up. Oh, I see why. Oh, okay, I was making a mistake. Never mind. It's there.
okay, we've got it. We're on the Wolf Riot star, the first one.
Should be soon.
Okay.
There it is. You can see it. I see it now. Okay. It's just me being a little human error. Okay. I don't know if people have noticed something different about this one already, but it's actually pretty. The signature of a wolf ray is pretty visible. Maybe I'll take a second. Oh my goodness. To talk about that. Okay, I don't know if people can see this, but okay, we'll compare these two. So this is a pretty normal spectrum for a star. It looks like your classic rainbow. But if you look at this Wolf-Rayet, you can see at certain points, you can see the spectrum being brighter. So like tiny little beads. And those are actually a particular type of line called an emission line, where the element is actually emitting light at particular wavelengths. And this is what we see very strongly in Wolf-Rayet stars. So this is what the particular interest we have in these type of stars. So I'll just take a exposure of that.
Okay. So those represent elements that are very strongly ionized.
Yes, and they're very hot and very excited. That's the term.
Uh-huh.
And
Could you?
so that they're emitting light at that particular wavelength. So
Okay.
that's
Would
what
you
the,
be Would you
yeah.
be able to say what elements?
We will
in
see that
that. Okay. Oh,
once
you're
we
gonna get the
yep.
graph.
Yeah, we have to get the graph for this,
Yeah.
but because it's a little harder to point out. Try to curse over each of the beads.
Okay. Well, while we're waiting for the graph, could I
Yeah.
for a moment just want to tell people that right now the County of San Diego is in the process of adopting a revision to the county lighting ordinance, which will create a category of communities called Zone C, which Borrego Springs will be one because it's already a dark sky community, and Julian will be another, and any other communities in San Diego that want to become international dark sky communities will be able to adopt this lighting code for dark sky communities. And if people could comment, that would be great. You can send your comments to the Planning Development Services of the County of San Diego and tell them you support this. This is very important development. It's going to permit Julian to become an international dark sky community since we've cleared most of the other hurdles and opened the door for other communities. And actually, we'll be part of a whole region, which includes Anza Borrego State Park, the community of Borrego Springs, and Julian. And we're very happy about this. The process is going to be heard at the Board of Supervisors meeting, and they'll be voting on it in November. So if you want to know more about it, you can email us at juliandarkskynetwork at gmail.com. And also, if you send a commentary to the county, send a copy to us. We really appreciate it, and we appreciate everyone's support. So just wanted to slip that in. It's happening right now, and we're anticipating the process being completed by the end of the year.
Okay. Okay, so I think we have the graph now. Well, we have this is the exposure itself, and this thing over here where you see the beads, that is the Wolf-Rayet star spectrum, and here's the Wolf-Rayet star. This star, it has, if you're an amateur astronomer, you might be familiar with the Crescent Nebula. This is the star at the heart of the Crescent Nebula, and it's its outer layers are what created the Crescent Nebula. It's outputting a lot of gas, and this is what the spectrum looks like in graph form, and here it is synthesized. And you can see these very strong peaks at certain wavelengths all across the spectrum. And these are the emission lines from particular wavelengths. And if you look at the graph, you can already see this one over here is from helium. Very strong emission line from helium. Very strong emission line from hydrogen over here.
This is
and this is the very strong, it's not that strong, emission line from hydrogen at this wavelength. And there's other ones here. These ones, as you'll see, these ones are actually from carbon, and that one's from magnesium. But these are very strong. Basically what we can see here is these elements are emitting very strongly. And this is because, as Doug already said, Wolf-Rayet stars are very hot and they're very massive. So these stars aren't very stable. So they're emitting a lot of gas, and what happens is that gas gets very hot. And when elements tend to get very hot, they start to emit light at certain wavelengths, and that's how they release their energy. And so we can see the signature of that gas shell around the Wolf-Rayet star in the spectrum, and it consists of mostly very strong emission lines from those elements. And as you can see, when you look at a normal star like Vega or our sun, or the stars in Albireo, those tend to have absorption lines because that outer atmosphere is comparatively not that hot. But in a Wolf-Rayet star, the case is completely different, and you get what we call an emission line star, where you have all these very strong peaks coming from the elements, and that's what's special about this star.
Okay, comment. Jerry's pointing out this is a star at the end of its life cycle.
Yes.
Then Marty Wax wants to know what's up at 7150, I guess, on the graph.
Oh, over
7150.
I don't know. I don't actually know. There's actually know what elements at here, but it's most likely another.
I can't see the numbers. Is that the real dark part on the right side of the spectrum?
Yeah, it's at the very it's this line over here.
Uh-huh.
Yeah, I don't actually know what that one is. I just because it's more in the infrared, and so I'm more the ones in the visible light.
Does that represent generally more heavier elements, or?
No, any element has its own spectral signature, and those can be at every different wavelengths. But you can make some general associations. Yeah.
Okay, so question from, let's see, a couple of questions. Okay, David Decker. Wow, we got Jerry. How many elements have been detected in this star's spectrum? This particular Wolf-Rayet star. And Dave Decker has another. Well, I'll take one question at a time.
Yeah, so probably a lot. I mean, also another thing is it depends on how metallic the star is. So the more metallic it is, you're going to have more metals, and that's going to mean there's more elements, and that's a function of how old it is. But there's probably, if you name an element, it's probably in there.
Okay, Dave Decker wants to know the emissions from the photosphere or the chromosphere of the star.
So this is actually not. This is neither. This is just a gas shell around the star. If you look at the Crescent Nebula, I guess I can pull that out in Stellarium. So it is
So this is beyond the star itself. This is.
yeah, it's stellar winds. It's producing
Mhm.
it's outgassing a lot of gas, and this is the signature of that gas around it. So Crescent Nebula. uh, This is, if for people who are not familiar with this object, this is the object, and it's a pretty nebula. It looks like a crescent or a euro sign, and all of this gas is outgassed from this singular star at the center, and this is the Wolf-Rayet star we're analyzing right now. So that's what we're actually looking at in this spectrum, is the outgassing in the gas shell around the star. It is not actually a particular layer. It's a very stable star. It's outgassing a lot of
Yeah.
gas.
So it's almost really part of the nebula in a sense.
Yeah. So
And that's also in Cygnus.
yeah. Okay, so I think we can move to the next object. It's the one below the Wolf-Rayets.
Right. This is a different Wolf-Rayet star,
Well,
134.
not, we can go to the after those two.
Sorry. Okay.
The one after the Wolf-Rayets. Yeah.
Oh, the Ring Nebula, you mean?
Yeah.
Oh,
Okay.
okay. That we're gonna jump ahead of the other two Wolf-Rayet stars.
Those are backups.
Oh, okay. Okay. Yeah. All right. We're going on to the Ring Nebula, M57, then.
Yeah.
Which is a planetary nebula. A lot of you probably know that. And it has a star at its center. It's also, kind of one foot in the grave star. That's the end of its life. It's kicked out a major shell of gas, and but there's still a dwarf star in the center.
Yep. Okay, I think it should be there now.
And we have looked at the Ring Nebula before. You'll probably recognize its shape there.
It's there faintly. 1 second exposure. Another thing is the grating. It's taking light from the nebula, so in general things will show up fainter.
But most you're going to see the object right underneath its
This
spectral line.
This one we don't need a graph to see what's going on, so we're not going to do that.
Okay.
Okay, I don't think people can really see this. So let's start guiding. People don't know this is to make sure it's accurately tracking because we've been taking long exposures.
Okay. Well, there's the Ring Nebula.
Yeah, let me take. I think 30 seconds works, and we'll just wait for that to load. So the thing is, so spectroscopy, you're basically spreading out the light from the object, and the more you can get more of that light, the more signal to noise ratio, the more detail you can see in the object, which is why another reason why astronomers are hungry for aperture, because the more aperture you can get, the more you can analyze the spectrum. So let me see.
So big mirror or big lens.
Yeah, you need big stuff.
Yeah.
All right, I think it showed up now. So let's start here. This is just the nebula itself, and it doesn't look that great, but you can see it looks like a ring, and you can generally see that on the outside it's more red, on the inside it's more green and blue. And this is the spectrum. It's over here. And what you can see is just basically two shadow images of the nebula. One that's red over here, and that one that's green over here. So this red shadow image over here, that is from hydrogen. It's from the specific line called hydrogen alpha. And this is what it looks like. And the one down here is from oxygen. It's called oxygen 3, and it's at a more of a teal wavelength. And what you can see is basically from this very bare minimum spectroscopic analysis, the main two sources of emission from the Ring Nebula are from hydrogen atoms on the very outer part of the outer part of the nebula, and from oxygen atoms that are more concentrated inwards. And that's a signature of a planetary nebula. You tend to have this kind of hydrogen on the outside, oxygen on the inside, and that's because oxygen is the heavier element. But So this is one way to analyze the composition of a nebula. Take its spectrum. And it's pretty clear here, I would say. Yeah. So
Okay, anybody have any questions about the Ring Nebula or its composition or anything?
What was the question that Dave
let's see. Okay. Let's see. Looking for it. I think we answered, unless Dave, if we didn't answer your question that you raised a while ago.
Okay.
Repeat it.
If there's no questions, we can just move on to the next object.
Yeah. People are talking about electronic assisted astronomy. That's actually what we're doing right now.
Yeah. Well, this is just taking exposures on the spectrum with the wide field grating.
Yeah. Yeah, for people who are new, I just say this virtual star party we're doing tonight is much more science oriented. We try to vary the star parties and do different things. So this one is a little higher level scientifically, and this is an area that Vivek has done a number of projects in. So we had a presentation at the Julian Library about it, and this is kind of building on that. We are going to have a star party next Saturday that will be a comparison of viewing the sky from two different areas. San Marcos and Julian will be doing it simultaneously, and imaging from both places so you can see the effects of light pollution and its absence relatively in Julian.
Okay.
And then the Saturday after that, we're going to have a more general star party. Be a sky tour.
Okay. Yeah. We can go to the next object.
Okay.
I think it's another planetary nebula.
Yeah, that's the blinking planetary nebula.
Okay. Yeah, we can go there. Then.
Okay. Kathy Hansel is with us. Great to have you with us, Kathy. Kathy's an activist has attended the IDA national meeting and has really contributed a lot here in San Diego County.
Should be going now. Okay.
And I think Kathy may have invited some of the people who are with us tonight.
This one's a little more interesting in terms of what's going on with the central star of the planetary nebula.
Okay. At the center of the blinking planetary nebula.
Yeah. Okay. Hopefully people can remember what the Ring Nebula looked like, because we're going to compare it a little bit. Okay. So let's take...
Oh, I think I see a nebula.
Start tracking again. Oh my goodness, there's no guide stars. Okay, let's go back. Okay, I'm gonna take a long exposure of this. This needs a very long exposure. But if you can already see, it's the same picture.
Oh, okay. I'm sorry. I found Dave's question.
Yeah.
At least one of his questions. Okay. What is your grading? What kind of grading are you using and what camera?
Okay, so the camera I'm using is, camera I'm using is an ASI 533 MC Pro. I think I got that like, 3 months ago. It's atypical. It's a square camera. It's very sensitive though, so. And I'm using it because color is more easier to see what's going on in terms of explaining spectroscopy. It's a cool camera too. The grading is something called a Star Analyzer 100, so that means it has 100 lines per millimeter, and it's pretty low resolution spectrograph, so you can see a very, very wide part of the spectrum at a low resolution. So.
Okay, we have a question from Stephen Opgenorth. What is the very faint dark blue or violet spectrum line just below the Oath? O2, or it's O3, I think. But
is it about in the blinking planet?
I'm not sure. I think
Well,
it's
I'm gonna
if it's
assume
the current object or the last one, actually.
I'm gonna assume it's the blinking planetary. But so this is the blinking planetary. It's a planetary nebula, just like the Ring Nebula. But there's a difference in that you can see the central star is very much there, and that's because this is at a much more earlier stage of evolution than the Ring Nebula. So this planetary nebula has basically, in the cosmic timeline, it has just formed, and the star is something called an asymptotic giant branch stage, and that means it's right now shedding off its layers and to become a white dwarf, which is the central star of a planetary nebula. So what the difference you can see here is that you can see the spectrum of the central star, while in the Ring Nebula, it's a white dwarf, it's much fainter and you can't really see it. But we can see basically the same signature of the hydrogen alpha from the hydrogen. Tends to be, in this case, it tends to be more in the center, while you have the oxygen down over here, and you can see the composition of the nebula itself. While you have the spectrum of the central star itself, and we can use that to analyze, what's going on in that star. And at this resolution, you can't really, it's just going to look like a typical main sequence spectrum, but at a more high resolution, you can see study what's going on with the star. So this is at a slightly earlier stage of evolution than the Ring Nebula, and you can see more of a central star.
Okay, I think, Stephen had his question was about the Ring Nebula, I guess. So sorry about that. We didn't catch it in time. But if you have a question about this nebula, feel free.
Wait, what was the question about the violet something?
Yeah, I think so. About the certain lines. I'm trying to find that again. Yeah, the very faint dark blue or violet spectrum line just below the O3. I assume it's got O2, but I assume he meant O3.
Okay, well, that's going to be just the spectrum of the white dwarf. It's a little fainter.
Okay.
The central star of the Ring Nebula, but that's pretty faint. Yeah, and here you can see it's much more strongly.
So it's just that with the Ring Nebula, the central star is much more depleted.
The Ring Nebula, it's basically just a white dwarf now. It's just here it's not. Another thing you can see the signature is the hydrogen is more in the center. It's because it's still in that earlier stage of development. So, and a lot of what happens in a planetary nebula is also affected by what stage the star was in when it started this process and stopped fusing, or how it interacts with the matter around it, and that produces the different shapes and morphology of planetary nebula. You can see this is much more different structure than the Ring Nebula looks like, but
it's more spherical looking.
It's also a little smaller. I think there's going to be different distances, but in general, I think this is a smaller planetary nebula because it's still in that earlier stage. Yeah. Is there anything else in the chat?
Let's see. There was a comment from Fred. There was a spectra superimposed, I guess, talking about the Ring Nebula, I guess.
Yeah, that's the central star.
The central star, yeah. Okay.
Or maybe it was a background star. I mean, as you can see, if you look at the field, there's spectra everywhere from all of the background stars. So if you have a grading like this, that can be a little issue. You have to do some workarounds to isolate the spectrum, but I'm not going to worry about that tonight.
Yeah, there are a lot of spectra, which means there are a lot of stars there. Yeah.
Yeah, we're in the Milky Way, so there's a lot of stars in here.
Pretty, dense area. Okay, so we're going on to the blue snowball.
Yeah, another planetary nebula.
And it's one of those things that a deep sky object that when you look at it through a telescope visually, you actually see color.
It's bright enough, yeah.
Yeah, most as people who have used a telescope to look at deep sky objects in the sky will know that most of the time you don't see very much color unless you have a really big telescope and you see a slight amount of color. But the blue snowball is distinctive. It's bright enough that you actually see the blue. I remember the first time someone showed it to me, I was like astounded. I was like, wow, there's color there. Usually you only get that with a camera.
It's normally a general trend. If it's a pretty bright, it's like the surface brightness, like the nebula itself, if it's pretty bright, that can trigger the cones in your eyes more, and you can see the color. And it's also dependent on aperture, of course, because you need the light to be able to see the color. Okay, it should be somewhere there. Yeah, the alignment's a bit more dodgy tonight.
Okay, well, there's a star there.
There's something there.
Yeah, okay, something's starting to show up a little more.
Well, I can also do the other technique. Let's see. There's a workaround around this. The problem I'm having here is this is a very high focal length telescope. It's a C11, so it has a focal length of 2800 millimeters. So, and I'm using a camera with a smaller sensor, so that makes finding things a little more difficult.
Yeah, we got a small field of view.
Yeah, so I have to just do regional alignment.
Okay. Well, there's a star. I guess that's the star you're going to use.
I did. Yeah. Now I'm gonna go. Now I can actually go to the nebula.
Okay. That's giving a reference point to the telescope mount.
The struggle of an SCT. I think it's there now. Or I'm seeing things. That's also possible.
Well, there's a star right in the center.
Oh, I see. Okay. Huh. I think that is it. More bearing with us. Oh, there it is. Okay, got it. My goodness.
Okay, got it?
Yeah.
Okay, you
It's
spotted it.
It's a shame for people who know what plate solving is. It's a shame that I can't use it.
Yeah, that would make it much easier for the telescope to know where.
But I think, yeah, this is pretty. Here it is. Here we go. Finally.
Okay. Yeah, I see something up there at the top. Okay, yeah. It's coming down to the center. Okay. All right. Let's welcome the blue snowball.
Let me start.
Oh, there. Okay. Yeah. Now we're seeing some color.
Oh, great. There's no guide stars. That's wonderful. There we go.
You have to.
Okay, got it. All right. Okay, I'm gonna start taking exposure. 60 seconds, maybe. Yeah, that's a little too. Okay.
And that color is not fake. That's the real color. It's pretty amazing.
Well, we'll see a longer exposure soon. So.
Yeah.
The struggle of spectroscopy.
Yeah, and that nebula, it has what looks like a number 3 or an E inside. the nebula.
It's got quite a lot of structure in it. We can look at that.
Yeah.
All right. All right. Here, that's much better. Okay. So this is the nebula itself over here, and you can see the structure as Doug was talking about, and you have a.
Can we zoom in a little bit on it?
I think I have, yeah. So
okay.
Inner shell, and then an outer shell outside of it, and then if you.
Oh yeah, there's you can see the detail.
And
yeah.
if you look over here, at this red, the red here, same signature of hydrogen alpha, and at the more bottom we have the same signature of oxygen, and you can see distinctly where these elements are located based on the spectrum, and also because they're associated with a particular color, we can also use that to.
So there's way more oxygen than hydrogen?
Yeah, that's a general trend of planetary nebula. They're very strong. The oxygen 3 line is very strong. Planetary nebula. There's a lot of oxygen. Yeah. And in general, I think this is what people are talking about. There's this violet and there's this green and red. That's a broadband component. That's just a general emission from the nebula. But what we're looking at is the very strong emission of oxygen and hydrogen lines from the spectrum. That's what we see in the planetary nebula, and that's how we deconstruct what it's made of. And if you analyze it with a more higher power setup of a higher res spectroscope, then you can start to see the other elements that are contained within planetary nebula. You can have nitrogen from nitrogen 2. You can have sulfur. There's a lot of different elements that you can analyze. But in general, the two strongest ones are hydrogen and oxygen. Yeah. Is there anything else from the chat?
No. People were just talking about the color of the moon last night and seeing Mars next to it.
Yeah. Okay.
I think you got a compliment for being able to find the objects from Jerry, given the focal length, which very long focal length, but it's
native C11. What can you do?
Yeah, but it's letting us see some of the detail too, and like in the snowball, the blue snowball.
All right. What's the next object?
Okay. Next object is V460 Cygni.
All right, this is the carbon star.
Right, it's a carbon star.
We're going to talk about carbon stars.
And this is an amazing star, at least to us humans.
So this class of stars.
Mm-hmm.
So can you read it should have an HIP number right next to it, right?
Yeah, it's HIP 10.
Wait, give me a sec. I have to pull it up. Okay, now say it.
Okay, the number is 107129.
Okay, I can go there now.
Okay, now this is a 6 magnitude star, which means you could see it with your naked eye if you were in Julian on a dark night. It is huge. It is its diameter is, hold on for this, 3.82 million times the sun's diameter. When I read that, I had to stop for a minute and blink. It's 2,000 light years away, which is not too far in the Milky Way, and it's also a variable star. And of course, it's a carbon star. So,
question. There it is. I think I got it. Well, all right. Let's get this centered. The spectrum that, if you notice, it's at the top of the. It's at the top of the
Of the screen.
Yeah, in general. Yeah, this top.
Oh, there we go. I think
it looks like it. Yeah.
Yeah, it's brighter than the other stars. Yeah.
This better be it, or else I'll look like an idiot.
Well, it looks a little bit reddish. It should be.
Well, it's not. I'm trying to look for the. Oh yeah, that's a carbon star. Okay, now I see that. Please go center. All right, let's get the guiding on this now. Dun, dun, dun. This one will need a, oh my goodness, not again. Okay, let's.
This is also in the constellation Cygnus.
Yeah, there's no guide stars. That's sad. Let's look for some. The other trouble of a C11, guiding it. I think that's a guide star. That's adequate enough. 2 seconds, please guide. It's gonna beep a lot. That's okay. I think people can bear beeping. Okay, let's get. We need to. We'll need the graph for this again to look at what.
Okay.
With it.
Yeah.
We're gonna hear a lot of beeping though.
Okay, so if you were to look at this star with binoculars or even your naked eye tonight.
But let's look at the star on the screen. I think it's pretty clear what the star looks like. Very red, and that's for a reason. It's because it's like it's like soot. It makes everything very red because it scatters a lot of shorter wavelength light. So the star is actually pretty red.
Oh yeah, look at that.
Of the carbon star. Okay, we got the right star. Now I have to do the color. Get the color off of it. Okay, let's save that.
So carbon stars are stars that have gone through several cycles of using up their.
Yeah. Okay, I'm gonna pull up the spectrum now. I want this to stop pinging me. Okay. Alright. This is the spectrum, I think. Okay, here we are. Let's get this in, and then you can already see this is a hot mess. And that is exactly what carbon stars are. Hot messes. What's that peak? 230. Okay. Now we're calibrated. I can close this and we can look at the hot sooty mess of a carbon star. Right, here it is. In its full glory. You already can tell there's a lot of infrared, and that's for a reason. It's because this star has so much carbon in it that a lot of these lower wavelengths, they're getting blocked severely by the carbon compounds. So what these stars are is that they originally start off like very sun-like stars. They're on the main sequence. They tend to be lower mass, and what happens is as they go into the red giant phase, something in their core, which we don't actually know why, carbon from the core starts going up into the outer layers of the star. And what happens is the carbon reacts with everything that's in the outer layers, and we get basically a hot mess of carbon compounds all over the star, and they result in this, which you see in this graph over here, is so many different peaks and absorption, a lot of different emission absorption lines, peaks and valleys, and that's due to the carbon compounds. And in general, because you can think of it like soot, a lot of infrared is there, and the lower wavelengths are much more fainter, and that's why the star looks like a very red, sooty appearance. And all of these peaks and valleys, those are from carbon compounds. So, for example, I know this one over here, that one, these peaks over here, they're from a carbon compound called diatomic carbon, which may seem strange to you because it is, but carbon stars don't care about what's possible. And all of these are from CH, carbon hydride. You can have triatomic carbon, 3 carbons reacted together. You can have carbon monoxide, you can have cyanide, lots of different, if it's a carbon compound, it's probably in there. That's basically what I'm getting at. this spectrum is actually pretty misleading. It's a low resolution spectrum. If you, for example, studied this carbon star with a high resolution spectrograph, which I do have, so I'm going to show that because it shows something. Okay, prepare for this graph. This is the spectrum at high resolution of a carbon star. This is not noise. These are all the compounds in the star. Yeah. So.
Okay, we have a question from Dave Decker. You're showing data up to about 9,000 angstroms.
Yeah.
Is that meaningful data for this low resolution view?
Yeah. So so my camera does have some sensitivity in the infrared, so we can actually study the bit of infrared in here. Yeah, it's a low resolution, which is why this is more smoothed out than it actually is supposed to be, because this is high resolution. This star is essentially a hot mess in space, but I think the graph already makes it clear. You have all of these carbon compounds. This is all because carbon starts leaking from the core into the outer layers, and there's quite a lot of carbon stars, like a few hundred in the sky, and these all tend to have all of these different variety of carbon compounds. It's like a carbon forest, and it produces the weird spectrum you see here and this. Yeah. And that's why carbon stars are very interesting, because this is very strange for a star.
So it's kind of like recently with all the smoke in the air from the fires, the sun started looking red because of all the carbon flying around in the air.
Yeah, it's this, but it's like that, but it's to a more extreme degree in a different cause, of course. But yeah, it's very sooty stars.
So would carbon stars account for the amount of carbon that we have on the Earth?
Well, a lot of the carbon can come from other. Yeah, you can have. Well, the thing is, the carbon is usually when we have carbon in a star, it's usually locked in the core itself, because that's
it's heavier.
Star. Yeah, like white dwarfs, they contain a lot of carbon in them, and that's where usually they're all locked. But yeah, carbon stars can help spread all these carbon compounds throughout the universe and seed it across. Mm-hmm. So you have carbon from supernovae, but yeah, so this is where you get carbon.
So this is where we get some raw materials for organic compounds.
Yeah, but
yeah. So Fred has a question: would these carbon stars go supernova or just kind of peter out?
They're low mass stars. These are like red giants, except gone somewhere else.
They don't start out as giant. Yeah, it's only the supermassive stars that become.
These are more in the planetary nebulae track of stars. Yeah. So that's carbon stars for you.
So someday our sun will produce a planetary nebula. Then I imagine.
Yeah, it will. I mean, whether it's going to be a carbon star, you don't know, but yeah, sometimes this process happens. We don't know why, and this is the end result of what happens. All these carbon compounds all over the outer layers of the star, and they have a very interesting history and a very interesting, obviously, spectrum and very interesting composition, and for us amateur astronomers, very interesting appearance too. There's a carbon star catalog for people who want to observe these stars, look at their color, because they have a very distinct color.
Yeah, they're about the reddest objects there are in the sky, I think.
Yeah. Okay.
Once you see one, you don't forget it.
I think we can go to the next object now.
Okay. Yeah.
And if there's anything in the chat, that too.
Okay. Fred said the Terra Planetary. I don't know what he's talking about. TERRA, capital letters.
That's the Latin name for Earth.
Okay. Oh, Terra. Okay, like Tierra. Okay. Alan Croix, aren't these stars that have gone through their hydrogen and helium fusion cycles?
They're still in the midst of and they're still in that midst, and this is what happens during that midst. But eventually, yes, that's gonna stop, and we're gonna get planetary nebulae out of them. But
because when they run out of hydrogen helium, they're going to collapse. That's the point.
well, the core collapses. The outer layers will be blown off into space. Yeah.
Yeah. Okay.
What's
All
the
right.
next object?
Next object is the Pegasus cluster M15. So this is a star.
Okay, this is.
I assume.
Oh yeah, there's a particular reason for showing this. Yeah.
Okay.
It's not. Yeah. Okay.
Yeah, we have a couple of star clusters we're going to look at.
I think it's just one. Oh no, it's two. Yeah. It's two.
Yeah. So, as people probably who are amateurs or have been to some of our other virtual star parties, star clusters are usually stars that are gravitationally somewhat held together in one place and have a common origin. They're usually generally all about the same age. And they are among the more striking objects to view in the sky, too, through a telescope or binoculars.
Yeah, if I can find it.
Oh, you will.
Oh my goodness.
Oh, probably not as hard to find as the blue snowball.
It's not that hard to find, but it's about.
It's just a different part of the sky.
Yeah.
Yeah, where this is in Pegasus.
If all fails, I'll just do another alignment. That's not it. Okay. I'll have to resort. Okay, what's the star in Pegasus? We'll go back to another main sequence
detect
start.
some movement.
It's movement to do an alignment.
Okay.
Super annoying.
Yeah, just for everyone, the scope that Vivek is using has a real long focal length. It's just sort of like if you were using a camera and you set it at f10 or so, you would be, having a narrower field of view generally. And that's the case with the telescope. It's a f10. And so it magnifies objects that you see, but have a much smaller area of the sky that you're looking at through the telescope. So it requires more accuracy. It's a little more fussy about finding things, more challenging. And Vivek has his telescope set up in the backyard, so he's got to set it up, get it aligned, get everything working, cameras, and so on. It looked like something pretty bright that just flashed by.
It did, because it's what I'm looking for. It should be there now.
Okay, well, we should see a bunch of stars.
Okay, well, I'm gonna end it. Okay, that's good enough. Gonna get out of here. Please go now. Should be arriving shortly. Finally.
Okay. Okay.
All right.
An opportunity for a bathroom break there.
Then. Is that it? No. Great. Yeah, finally got it.
Okay.
There it is. Oh my goodness. How long did that take?
Oh, a couple of minutes.
Okay, that's fine. Okay, this is just gonna be a
Thank you.
very long finding time for something very brief. Okay.
Sorry for the sneeze.
Well,
I've got the windows open. The
da,
house
da,
is
da, guide star.
okay. I
That's
think
good
that's
enough.
on the right there. It's popping into the field of view. There we go. It looks kind of fuzzy. That is a star cluster. Yeah. Oh my. With a very bright center.
Okay. Well, the point here. Okay, so we're going to talk about once this exposure finishes, we're going to talk about the M15. We're going to talk about finding stuff in clusters, and generally we're going to see the spectrum of a lot of stars in a cluster. When it loads in 2 seconds. Okay, there we are. So, very high resolution image of M15. Not, and we have here the spectrum. In general, you can see these are main sequence stars. They're not very much particularly interesting about them, but this is.
There we go.
But generally, we can use this method to assess, try to pick out some interesting peculiar stars in star clusters.
Wow.
You can see the similar pattern in stars. They're all most of them are main sequence. They're gonna have pretty typical spectrums where it's basically a continuous spectrum with some absorption lines, but that's what we get out of M15. If there were any particular interesting stars there, we could pick out and say, oh yeah, here's this particular type of star. Like, oh, here's a variable star because it shows this specific spectral feature or something. But
could you just talk for a second about what you mean by main sequence stars?
So these are stars that are going around in the normal part of their lifetime, or they're just fusing hydrogen, and depending on the mass, that stage how long a star is on that stage, or really how long the lifetime of the star is, it depends on its mass. Higher mass stars last for only like millions of years, while lower mass stars can last for billions, like our sun, or very, very low mass stars can last for trillions of years, like red dwarfs. But a main sequence is generally where it's fusing hydrogen, and it's the main part of the sequence of a star's lifetime, which is why it's called main sequence. So.
And they're the most common star.
Well, yeah, because that's generally where a star spends most of its lifetime. Interesting stages where it's forming, or it's going supernova, or it's turning into planetary nebula. Those are much shorter parts of the star's lifetime. Yeah.
And our sun is a main sequence star.
Yeah, right. If you know what a spectral type is, it's a spectral type G2 star. It's white and it has absorption lines. It's a typical main sequence star. Yeah. But okay, what's the next object?
Okay, next unless anybody have questions about the cluster or the spectra? Don't see any. Okay. All right. We're going on to Cassiopeia M52. Sometimes called the salt and pepper cluster.
That's a backup. Next.
Oh, that's a backup. Okay.
Yeah.
I thought we were doing. Okay. Oh, that's why it has the parentheses.
Yeah.
Okay. What about the bubble nebula? Is that a backup?
Okay. Yeah. No, that's a nebula. We're gonna go there.
Okay.
Yeah. Okay. My alignment is good.
Good.
We get there.
Oh, you know the NGC number? I take it.
No, I don't.
It's 7635.
Okay, yeah, I remember that one. Okay, we should go there. The bubble nebula is a ionized hydrogen region, H2 region, and it just means that in general it contains a lot of hydrogen. There's some other gases in there, but it's general just hydrogen gas. Hydrogen, and it forms a nebula. And that nebula is called the bubble nebula. And hopefully we'll see that soon. Yeah.
And Fred threw out a riddle. Oh, be a fine girl, kiss me.
Yeah, well, that is the OBAFJKM are the spectral types that we use for main sequence stars. There's a reason why it's OBAFJKM, and it's because of the long history of astronomy, but yeah, so that's the sequence. O stars are the hot stars, M stars are the cool stars.
Right, and then the others are in between.
Yeah.
Okay.
It's in sequence of decreasing temperature.
Was that the Harvard Observatory that came up with that categorization? I remember.
Yeah, they're responsible for much of it. Yeah. But there was a long attempt at creating a standard, and it started off like A B C D E F, and as they tried to compile the standard, it became OBAFJKM, which is, and that's why you need a mnemonic to memorize it.
So you passed your astronomy 101 class.
Yeah.
Okay, a question from Christopher Sebald. Would you be able to differentiate tri-star system like Beta Perseid?
Would you tri-star Beta Perseid Algol? I think that's Algol.
Is that Algol?
I think that is.
Beta,
yeah.
Yeah. Okay.
So we know that Algol is a triple because of spectroscopy, and later on, through some very special methods of imaging, we were able to actually separate and see the individual stars in it. But spectroscopy is how we found out in the first place about it being a triple system. But yeah.
And it's a variable star, right?
It's a variable star because it's an eclipsing binary. So the stars go in front of each other and eclipse each other, which is brightness changes.
Yeah, imagine living in a planet in a system like that where you'd have an eclipse of one star by another.
Well, the way that Algol is, you don't want to live there.
Yeah. Okay. It's not prime colonization material.
Particularly. Okay. Another star alignment to find an object.
Okay, we haven't got to the bubble nebula yet, right?
No.
We're getting there. Okay.
The ghost is just decided to fail at finding anything. And now we can back to regularly scheduled programming. Okay, and back. We should be there now. That's it. Think so. I remember this now, so I think we're there. Just have to move it a little more down so you can see the spectrum. But we're actually not going to be looking at the entire nebula. We're looking at a specific knot, so like a very dense region in the nebula, and looking at that spectrum. And that's going to take a lot of exposure, so there are plenty of guide stars. Not surprising, it's the Milky Way.
Okay, Christopher, could you tell us where you're? I think you're a friend of Kathy's, it looks like. Could you tell us if you're in San Diego or where you are?
Yeah. So we're looking at a knot in the nebula, and what we'll be seeing is it should be hydrogen. We're looking at a hydrogen region, a nebula made of mostly hydrogen, and we'll be able to see that signature that is, hydrogen. Well, yeah, it tends to be the hydrogen. Hydrogen is indeed the most common element in the universe. Oh boy. Great. Checking the spectrum. Okay. Okay, so that's the.
Okay. Borrego Springs. Thanks.
This is the knot, but the spectrum is all the way up here. Great. I'll have to slew now to get the spectrum in.
Okay, that's your calibration star?
Well, no, that right now, no. I found.
Oh, there's the nebula. Okay.
I found the knot, but the spectrum of the knot is not in field of view yet.
Okay. Oh, well, we got Roger Monroe from Missoula, Montana. Welcome. How did you hear about it? Always interested in knowing how people find out about what we're doing.
Oh, please center. Okay, I think center. Like so.
Okay, great. From Abna. Oh, I got to give a shout out to Betsy Kanak for putting our star parties in the Abna Sandpaper newsletter. That's probably how we're getting outside of California somewhat. So thanks a lot, Betsy, for that.
Okay, we're taking a 30-second exposure of this. Hopefully we'll see something, but the knot's over here. It's gonna show up soon, but the spectrum will be somewhere over here in the field of view. This is a very faint object, so this is a little bit ambitious. And I think it just told me, nice. Okay, that's not what I expected. What is it doing? Oh, I lost the guide star, that's what happened. Ah. Okay, it's still there. The better guide star. Yeah, the tracking is very critical for this kind of setup. Alright, let's try that again. Is there anything in the chat?
No, just, thank you from Betsy Kanak from Borrego for sharing the program. We're certainly glad to share it. That's why we're doing this, and glad you're helping us share it, Betsy. And also, I just want to mention that I got a couple of copies of the Borrego Sun, which has a great front page article about Julian joining Borrego Springs and Anza Borrego State Park and becoming a dark sky place. That thanks to Ernie Cowan, who wrote the article. So I encourage people in Borrego to grab a copy of the Borrego Sun if you don't usually get it. So it talks about the process going on right now with the county. And
okay.
Again, I just want to tell people to, chime in on supporting the revision to the county lighting code, which is going to make San Diego County, especially unincorporated San Diego County, potentially a lot more dark sky friendly. Yeah, I'm sorry, go ahead, Vivek.
Okay, so we have the knot down here, the hydrogen knot below the star. But what we're looking at is, here's that section of the star, very faintly. I think some people can see that. You can see a mirror image of that knot, and that's from that's the hydrogen alpha over there. And the spectrum is basically just this hydrogen alpha mirror image. And so we know conclusively that knot's made of hydrogen. I don't know if people can see that very well. I'm taking a little longer exposure, but we can see the signature of hydrogen. And you also have the problem of this star's spectrum is also overlapping, but it's visible.
Yeah, they're right in line with each other.
Yeah.
So if your image had a different orientation, it would be easier to see the spectrum separately.
If the grading itself is dictating how. So I have the grading right now in this orientation. If I change the orientation of the grading, then this would change.
Okay.
So you can use that to try to get around this, but yeah. So you just have to rotate the camera train to get the spectrum to not cross-contaminate. But that's just the problem with this kind of spectrograph. It's just a grading. Like a professional spectrograph or a high power one, that's going to have a slit. So you only get the light from whatever enters that slit, and you position the slit over a star or the nebula.
So you can be more selective, yeah.
Yeah, and yeah, so that's what typically is used to study this kind of stuff. But for demonstration purposes, you can see quite a lot with this kind of grading to measure the spectrum. Measure's
Yeah,
almost done.
Dave Decker just wants to know if you're set up in Julian at Curiosity Peak.
No, I'm set up at home. I'm in San Marcos. We have 7 light pollution. It's SQM is 18.5. There's a gibbous moon. The sky conditions aren't amazing.
Yeah, but we're doing pretty well considering. Yeah, I'm in Julian. I'm just kibitzing here from Julian. Some of our star parties were both up here in Julian. Some were not.
Okay, this is much more clear. Here's the knot. All right, and then we have same mirror image of the knot over here. I think that's pretty clear. And that's how we conclusively know that knot is made of hydrogen. Yeah. And there's a dog.
Okay. Yeah, so the knot is, yeah, right there. Okay.
Yeah. Okay,
Yeah, so it takes some developing some observational skills, I guess, to really identify the knots and things.
Yeah, but I think we can move on now.
Okay. Yeah.
Yeah.
Okay. Navi B star.
Navi is a BE type star.
Okay.
Gamma Cassiopeia. Actually, I have to stop guiding.
Okay, so it's in Cassiopeia.
Yeah. It's Gamma Cassiopeia. There's actually a nebula around it too, but we're not going to be studying that.
Okay, is that one of the stars that forms the WM or 3?
It's one of it is.
So if any of you are familiar with, I know some of you are, with the constellation Cassiopeia, there's the brightest stars form like a W or an M, depending on what position it's in the sky as it swings around Polaris. And this is one of those stars.
I just have to find it in the hand controller. Okay, got it. Oop. Should be there somewhere. Nope. Okay, we're gonna have to go to the next object.
Okay.
My house is blocking it.
Okay, well, I guess
yeah.
We could wait an hour or two, or is it going down or going up? Okay.
It's,
or saw off the corner of your house.
Yeah.
Okay.
What's the next?
Okay, the next is Neptune, planet.
Okay, that's.
Oh, we're coming back into the solar system.
Okay, this.
And Neptune's got some color to it. So we will know it when we see it. It's going to be kind of blue, right?
Yeah.
Okay, Betsy. Okay, let's see. Betsy has on the next commercial break. Tell us more about Curiosity Peak Observatory. Well, I can do that right now, I guess. Well, Curiosity Peak Observatory is a amateur astronomy observatory that we built. Todd Rogelstad and I and another friend built we started in the fall of 2013 and finished it in the spring of 2014. There was a lot of wind, rain, and snow in between, so we had to do the construction when it was weather permitted. It has 3 positions in it, and we do astrophotography there, which there's three mounts and room for 3 telescopes. Roy Hansen is one of the astronomers that uses it frequently, as is Vivek and myself. Fred also has used it quite a bit and sometimes uses it remotely, since he's now living in Baja California. We have an outside area next to the observatory, which is for visiting astronomers
Well,
and
that's where I tend to set up.
yeah, and that's what how we met. Vivek started coming up and using it, and we got to know each other. Um, so we really look forward to sharing our space. It's on a hilltop in Julian, away from the town, and not too much ambient light there. The observatory itself is a roll-off roof, which is a very simple kind of roof. It just has four casters that it rolls off onto a gantry structure that holds the roof while it's not needed over the observatory itself. And we're still using it frequently, going strong. So I don't know what else to say.
There's no guide stars. I know this already. The Milky Way anymore. It's not gonna work. Okay, I'm just gonna have to take an exposure then. But that's Neptune on the screen, and it's spectrum. You can already kind of see it. But I want to analyze this. So.
Okay.
And
Oh, just one more thing I'd like to say. Curiosity Peak Observatory has a website, so I encourage anyone who's interested in knowing more about it to go to the website. You can see how it was built. You can see images that we've taken there and have taken over a period of time. So that's all. That's my commercial for Curiosity Peak.
Yeah, I think in that I should also mention 3, 2, 1. Oh, what the hell? Nope. That's not usable. Okay, I have to try that again. Where is it now? Yeah. What? I don't know why I did that. Okay, we'll try this again.
And we may get a glimpse of Neptune's largest moon.
We already technically got a glimpse of it.
Okay.
Go back to that failed exposure.
Okay, well, it might come back.
Here's that. If you notice that trail over there, that is Triton's trail along Neptune's trail.
The spectrum.
Well, we can't really see it here, but if you expose it for long enough, you'll see Triton spectrum. But that's most likely just going to be basically a copy of the sun spectrum because it's reflecting the sun's light. So that's still.
But would it have some absorption lines for what is being absorbed in its atmosphere? Or?
Yeah, there's going to be a little slight deviation, of course, but it's generally going to be the same. Okay, I think this is more usable, so I'll try this. But if you notice, there's a Neptune is doing the same thing. It's reflecting the sun's light, but it's also adding its own contribution of absorbing some of that light.
Oh, there's Triton.
So Neptune is also reflecting the sun's light, but it's adding a little something because some of the compounds in Neptune's atmosphere are absorbing that spectrum. So we'll be looking at absorption lines caused by, well, Neptune itself. So here it is, Neptune. There's Triton over there. And now we can analyze Neptune's spectrum. First have to get the color. So that's the latest image.
And we're seeing some absorption lines, I think, aren't we?
Yeah, there's going to be absorption lines from the compounds in Neptune's atmosphere.
Okay. Yeah, Vivek just pointed out Triton for anyone who hadn't seen it yet.
Yeah.
Yeah, it's really cool that we can see one of Neptune's moons, considering how far away it is.
Okay, let's analyze it.
Does Triton have any atmosphere?
Does Triton have an atmosphere?
Or is it just a rock?
Well, it has a. Well, technically, everybody has an atmosphere.
Okay.
Oh my god, what is going on? Where's my mouse? Okay, that's better. Let's calibrate this so we can understand what's going on. That peak is at 201. Apply. Okay, let's look at the spectrum. So, the sun spectrum. This is the
Wow.
spectrum with some of Neptune's contributions. So it won't. So what we're seeing mostly here is methane. So methane absorption, some ammonia absorption, but in general it's mostly methane absorption, and that's what these big giant values over here are. So from this very bare spectroscopic analysis, we can conclude that Neptune contains methane. But if we take more data, we analyze it, we do high resolution, we can start to see some other compounds, but we have to compare it to the sun spectrum because that is the source of light, and we can use that to examine the what's going on with Neptune. And
I see. Fred's cracking more jokes. Okay, sorry. Just had to laugh.
yeah, but so yeah, that's these signatures over here are from the compounds in Neptune, mostly methane, and yeah.
Okay, so major methane supply.
Yeah, for sure. There's actually a filter you can get, and that can show you what what things look like in these CH4 methane absorption bands. There's a filter for that, and the planet.
CH4 is methane.
Yes, yeah.
Yeah.
And the methane, and what you can see is very interesting structure on the gas planets, on the gas giants, and yeah. So if you look at Saturn, for example, when you look at it in a methane band filter, you'll see the rings are very bright because they don't have methane, because there's no methane absorbing it. But the Saturn itself is darker. And if you look at Jupiter, you can see a lot of different structure for methane, where you can see where it's rich, where it's not rich. And if you look at Uranus, Neptune, it's just going to be dark. It's all methane. So yeah, studying filters in these bands can really show you a lot about what's going on with the planets, and that's why they exist. Yeah.
So that would make some interesting planetary photography too. Then I guess.
I mean, I have it. I can
Uh-huh.
I can show that, but it's deep in the annals of what I have. Let's see if I have a Saturn in here. Do I have one? Oh, here we are, CH4. Can you see that? Yeah, so this is Saturn in the methane band filter, and well, you can tell from here, the rings don't have methane. That's already established. That you can see differentiation in the bands based on their methane concentration.
Oh yeah.
And for Jupiter, you can do the same thing. I don't think I have it here right now, but yeah, there's a lot of interesting things you can do with spectral lines.
Yeah, so that means there's a kind of a faint or somewhat strong methane band around the center of Saturn.
Yeah, well, that's just
a belt, I guess.
It's just basically showing you where methane is stronger. So
yeah.
Darker it is, the more methane it is. So.
Oh, the darker, okay.
Because it's an absorption band.
Yeah.
The rings don't have methane. That's why they're very bright.
Okay. So the bright area in the center was where there wasn't so much methane. Okay.
Yeah.
I mean, something else, ammonia or.
Well, yeah, just other compounds. There's a lot of different compounds in the atmospheres of the outer planets. Yeah. Okay, what's the next object? Or is
okay, after Neptune, we have a carbon star. Are we going to do that? Or is that a backup?
I mean, I think we can move on. What's the next one?
Okay, we've got the satellite galaxy of Andromeda,
Yeah, right.
M32.
Yeah, Fred actually asked a question about this one, so
Oh, okay.
like before the star party.
Oh, okay. Oh, right, about taking spectra of trying to
And galaxies.
of individual stars or of galaxies. What you?
Well, we'll see if my alignment allows me to even find the thing. Da, da. Let's do another alignment.
Electronically assisted star hopping.
That is what it is. When you don't have when you can't use plate solving, because it's all messed up by spectrums. That's Merak.
Mm-hmm.
Also pretty spectroscopically interesting. Okay.
Doesn't matter that it's not centered.
I just want to see.
Yeah.
Okay. Merak is very close to M32.
Oh, there we go. Yeah, that's Mirai.
Oh yeah, you're getting a lag. That's why. Yeah. Found M32. Just have to center it now.
No atmosphere. Okay. All right, Dave. Thanks for joining us.
Yeah, we're almost. Okay, we're M32. Okay, got it. Okay, now I have to find a guide star now. Nothing. Is there? Okay, we can't use guiding here either. No guiding. Walking dangerously. Okay. I'll just take a. But yeah, M32 is an elliptical galaxy, so that means it's just a very dense cluster of stars, big giant cluster of stars galaxy. But it doesn't really have much structure to it. It's just a sphere, ellipsoid, but what we're gonna look at is the spectrum of said ellipsoid and see what it looks like. And if you know what, if you already seen M15, you know what this is gonna look like. That is the spectrum of M30. This is the elliptical galaxy M32. It's a satellite of Andromeda. So Andromeda is at the very bottom, is more to the bottom of the screen. But here's a spectrum of M32. No surprise, it just looks like a spectrum of main sequence stars, because that is what it is. It is just the average spectrum of all of the stars in M32. Plus, as Fred was talking about, he was asking about what that's going to look like. So it is going to be the spectrum of everything that's in there, all of the gas, dust, and main sequence stars. In general, it's going to be just dominated by all of the main sequence stars. There are some. This is interesting. There are Wolf-Rayet galaxies, and those are basically galaxies. Those are galaxies that contain so many Wolf-Rayet stars that the signature of a Wolf-Rayet star is very present in the spectrum of the galaxy. So they're called Wolf-Rayet galaxies. Those are very interesting because somehow they've created so many Wolf-Rayet stars that the spectrum is just basically like a Wolf-Rayet star.
Is there any theory about why you have a galaxy that has so many Wolf-Rayet stars?
Well, it's to do with galactic evolution and starburst. Like you need to create a lot of hot massive stars. So it's going to be pretty young, and it's going to be full of a lot of gas to produce those stars.
Hmm.
But there's still more details to crank out. But yeah, so of course, there's nebulae and gas and dust. So there's a lot to a galaxy, and then you can analyze what's particularly going on. But it's
Hmm.
just gonna be the averaged up sum of all the components of the galaxy. And for M32, it's just a main sequence star spectrum.
Does M32 have any characteristics that are caused by the fact that it's orbiting a much larger, massive galaxy?
In the spectrum,
Well, in general, just
well, what happens is it's gravitational inbound, so that's the effect. But in general, it doesn't really affect what's going on in the galaxy.
mhm.
In this context. In other contexts, absolutely, a galaxy can really do things to this galaxy. But in this context, it's an elliptical galaxy orbiting Andromeda, so there isn't a whole lot going on besides. So,
Okay, Fred's got a question. Would that mean that the spectra of that galaxy is primarily emissive?
of a Wolf-Rayet galaxy, yes.
I don't know if you meant M32
Well,
or
M32 doesn't have any emission lines, if you look.
okay,
Can't really see any. But a Wolf-Rayet galaxy, absolutely. That's the signature of a Wolf-Rayet star. You're gonna,
okay.
yeah.
Well, I think you probably answered his question, whatever it was.
Yeah, I was trying to do that, yeah.
Yeah.
But,
Okay,
yeah.
another question. Can you detect redshift pretty close, so maybe your tool
Yeah,
isn't sensitive enough?
yeah, so of course you can see redshift and blue shift on these galaxies if you have the appropriate tool. Um, with this particular, in this grading, not really because it's very low res, but with a high res spectrograph like the one the other one I have, yeah, you can. It's very clear that you can see that redshift or blue shift. In this case, it's a blue shift because it's Andromeda, because it's coming.
Hmm.
So there's a blue shift.
Because it's coming towards us.
Yeah, you can detect that blue shift, and you can measure what that blue shift is to get the velocity. So for Andromeda, I think it's around 300 kilometers per second. So, and that's going to be that's going to be very detectable for us. So, if I had the other spectrograph on, you could definitely see that big gap between where the spectral lines is supposed to be and what their rest wavelengths are due to the blue shift of the galaxy. But this thing, not really.
Okay, another question from Alan Kreutz. Hope I'm pronouncing your name correctly. Maybe comparing HA with the star next to it.
Yeah, if we yeah, so on a that would definitely be a technique for, yeah, that's, you compare it with a spectral line with the rest wavelength. It's just that this grading it's 3.3 angstroms per pixel, so this doesn't really have the resolution capability, resolving capability. And also, the other thing is, it's not a slit spectrograph. You need to have a slit because that HE line is going to be blurred out because this is not a point source. This is a galaxy. So this type of setup cannot do the redshift measurement. But a slit spectrograph, yeah, it's very evident to see the blue shift. Yeah,
Okay, well,
I think we can move on, right?
yeah, we've got one last object, Uranus
Let's see.
planet.
Well, I think hopefully we can see that. Not too sure about that though. There's a problem.
Yeah, tree.
Yep.
Oh no.
This is what it's like imaging from my home.
Well, this is an eclipse.
Yeah.
An eclipse of a planet by a tree.
It's very interesting to look at, obviously.
Okay.
It actually is. You can see it though. Oh yeah, no, it's not blocked by the tree.
Oh, okay.
Problem is if I can even see it though. I need to do a star alignment.
Okay, we're gonna do a little more star hopping.
Yeah.
Okay, for people who are not amateur astronomers, when we say star hopping, what that means is we go to a star and tell the mount by means of its hand control that it is pointed at a particular star, and then it takes note of that, and then it's able to
Well,
find other objects in the neighborhood
well,
by,
that's a star alignment. Star hopping is basically using stars. Is basically when you have a finder scope, you use stars to look to
yeah,
object manually. So
yeah,
use the
you're right. I
stars
was
as a
describing
pattern.
yeah, yeah. What I was talking about was with a go-to telescope that has
That's a star alignment. Yeah.
yeah,
That's yeah.
yeah. When people do star hopping, then they're basically visually locating objects in the sky using other
Yeah.
objects, using familiar stars.
Here we are, Uranus. If we expose for long enough, we can also see the moons on here too. There's like a lot that are visible, so that should be fun. And you can see the same characteristic of methane. More jokes about that. Don't. I'm kind of sick and tired of hearing about this planet.
Oh, okay. Yeah, methane jokes and yeah, okay, yeah.
Yeah, it's not. It needs to center more.
Well, maybe Fred can tell us about the Uranus and how it got its name
About Georgium Sidus.
without making the most ridiculously lowbrow joke in astronomy.
Yeah, that's just
Okay,
a terrible joke.
let's see. Go to Betelgeuse, then move down to Almanac.
Oh, he's describing star hopping for some
Oh, okay,
object.
yeah. Ask William Herschel.
Okay, I'm gonna take an exposure now, and we should be able to see its moons. 20-second exposure. We'll get it focused down here. Guiding is normally okay, except it's trash around here. 15, 16.
Okay, so we're looking at our outermost planet, at least official
Oh,
planet.
we'll need a longer exposure to get the moons.
We're gonna see some moons.
Yeah, I need a long exposure though. But yeah, there's plenty of moons. There's a lot of moons around Uranus.
But how many of them can be captured
I think
easily?
like 5 or 6 should be there or something.
Oh, okay. Oh,
We can actually look at Stellarium for this and see what's there. Well, let's look at Neptune really quick, because, yeah, Triton's over there. But let's look at Uranus, there's quite a lot. All of these. So we should see around like 4 moons, depending on how much shows up in this thing.
Mm-hmm. Oh boy.
But they're faint. No question about that. Very hard to capture.
Yeah.
Here we go.
Uh-huh. Well, it's definitely a planet.
Never mind. What is it doing? Oh my goodness. Doug, are you seeing the guide graph?
No.
You should see it soon.
Pretty crazy.
You'll see it soon.
Okay.
I'll know when you talk.
Okay. Fred answered the question sort of about Uranus. Greek mythology, a personal choice of William Herschel. Okay.
Yeah. Well, he didn't talk about Georgium Sidus.
No.
They originally wanted to name it Georgium Sidus, George's star, after King George. I think the third.
Oh. Really? How many things have to be named after King George?
Not enough. Oh my goodness, this guy is there. Okay, well, okay, I think you can see a moon here. I think we have to skip the moon part. The guiding is too trash for the moons.
Okay, I see a little something up there by the spectrum, but
Okay,
that's
well, okay. I think maybe people see this, but there's one moon over here. There's another moon over here.
oh, okay.
I don't know.
Is that
I see it, but I don't know if people can see that. But yeah, this is just the spectrum is
okay.
difficult.
Yeah. Well, what?
The guiding is just not good enough. Yeah, guiding matters. You need to be able to get a.
Is that affecting our ability to interpret the spectrum?
Yeah, because the spectrum will get blurred out.
Yeah.
So it won't be as good as it won't be that good, but it'll be usable.
Okay. We got a comment from Fred Delgado. No.
What about no?
I don't know. N-O, does it mean no, or are those initials?
I don't know.
Fred's giving us an enigmatic chat here.
Maybe you meant no, I don't want it named after King George. Who needs more names like that? William Herschel was a man of his time. Have to please the king, you know.
Yeah. Yeah. An unfortunate part of being a scientist.
Okay, let's look at the spectrum of. Let's see. Okay, I think you can see that spectrum. If you notice, it looks identical to Neptune because it is. We have methane, methane, and methane. You have the absorption from methane.
Oh, Fred couldn't see the moons of Uranus. Okay. All right, Fred, thanks for joining us. Have a good night.
Oh yeah, this is the last object. Yeah, but I guess you can see a hint of hydrogen beta because that's the signature of the sun. But
Okay.
mostly dominated by methane because that's what Uranus has got.
Mm-hmm.
Just like most gas giants. Yeah.
Yeah, methane is abundant in the solar system,
Yeah.
especially the outer solar system.
Okay, yeah. I think that concludes Spectroscopy for tonight.
Yeah. Okay. Well, we thank you everyone for joining us. It was great to have people return as well as having some new folks. And if you have any input for us, send us an email at curiositypeak@gmail.com.
I need to cut down a tree.
Yeah, if you want
Well,
to
actually,
comment.
it was the house.
It was a house. Okay. Well,
The house, no Gamma Cassiopeia because of the house.
yeah. Well, when Vivek's dad bought their house, I don't know if you were interested in astronomy yet.
Well, it's just the
But-
backyard, you know.
Yeah.
Got your
right.
limitations.
Yeah. But, that's why it's important to have places like Julian with a dark sky for people to come up here and get away from the light pollution and be able to see the universe, whether it's with your naked eye watching a meteor shower, comet, as many people did recently, or bring a telescope up here. When we get over this pandemic, we'll be once again welcoming visiting amateur astronomers to come up and set up next to our observatory. And we'll be putting on in-person star parties. But for right now, we're doing what we can by doing these virtual star parties. So keep in touch with us. We'll be doing one next Saturday. It'll be a comparative light pollution experience of suburbs to Julian. And well, good. Mike McKeague says, makes me want to take up spectroscopy. Okay. Yes, you need another hobby, Mike.
There's so many subdivisions within astronomy that you can all explore. You have got yourself visual astronomy, astrophotography, which itself can be deep sky or wide field or planetary photography. You have spectroscopy, asteroid hunting,
Yeah, comet hunting.
exoplanet transiting, and
Yeah,
transits.
variable
There's
star.
just a lot you can do in astronomy, so be careful not to spend too much money.
Yeah, also outreach. Did you mention outreach?
Yeah, well,
You did.
outreach can be done, with, visual astronomy, where you show people the stuff directly with their eyes, or, EAA, electronically assisted astronomy, which is partly what we've been doing with the star parties. So, yeah, there's a lot you can do. But you don't have to start with any of that. You can always start with a good pair of binoculars and do some visual astronomy, of course.
Yeah, in fact, that's highly recommended because
Yeah, to start out.
Yeah, you know, a lot of people just jump into getting a telescope and getting a pair of binoculars and learning some constellations, sweeping the sky. There are a lot of a lot of objects in the Milky Way you can see with binoculars, star clusters. You can see the galaxy. There are galaxies that you can see with binoculars. Certainly, the Andromeda galaxy is spectacular with a good pair of binoculars. And get a planisphere, which is a good way to learn the sky. Costs about $12 with it. We sell them the Julian Dark Sky Network, and it has a wheel. You spin it and set it for the time of the night and the day of the year, and it shows you what's up in the sky and the brightest stars and where some of the binocular astronomy objects are.
Yeah.
So.
Okay.
Yeah.
All right.
All right. Well, thanks. Huh?
Anything in the chat?
Yeah, well, a lot of goodbyes and thank yous from Roger, Alan, Betsy, Stephen, Mike McKeague, Christopher, Kathy, and Fred.
Okay.
And, and I don't know if Gary's still there, but he may have gone to bed by now.
All right. I think we can end the stream now.
Yeah. All right. Thanks, everybody. Take care.
Thank you.
Hope to see you next Saturday night.